second meeting with Bayesian statistics, and in particular our second meeting with one parameter models in STAN. Hopefully we'll have a shorter lecture today. We'll be discussing mostly modeling of discrete events, which number can be represented as an integer, and we'll be interested in how many events can occur in certain period of time. We'll focus on two examples, which will discuss the methods of how we start creating a Bayesian model from more simple ideas to more advanced. And we'll start with uninformed prior distributions, and then we'll move to the more informed ones. At first we'll focus on the Poisson distribution. Poisson distribution is a probability distribution of expressing the probability of having a certain number of events that occur in a fixed interval, for example in a year, in a day, in a week, or in a certain area if we are considering spatial distribution, and those events occur with a constant mean rate and independently in interval or in area. So generally such things can happen in multiple situations. We'll in a moment. What is more or less interesting, probability mass function is maybe less. This is a one parameter model with parameter lambda, and x is our number of events that can occur. So this is a discrete, x is a discrete variable, and what is interesting that mean and variance are both equal to lambda, and because variance is lambda, standard deviation will be a square root of lambda. And this is useful for analyzing models, especially in more complicated cases, because if our data does not show the same result, that both mean and variance are equal, then maybe something else needs to be used than Poisson distribution. However, if they are approximately equal, then it's a good idea to model it with Poisson distribution. And where we can use it? Well, we can use it in many multiple situations, and among the others, those can be numbers of accidents, numbers of that can happen in a city, number of police stoppages of drunken drivers or speeding drivers in certain times. It can be numbers of customers, number of people going to a website in certain time period, or more technical aspects like losing packets during transmission, or other generally discrete events that are not happening in certain constant rate. We've got some multiple of ideas, and we have two of them today to discuss. And we'll start with maybe a little bit morbid question of how likely are you going to die on a plane, or how likely a fatal accident can happen during a flight. And if you know the classic 80s movie Airplane, which is a comedy classic of and parody of multiple airplane scares flights from that period, you know that anything can happen. People can get hysteric, but generally we go to a happy ending, even for autopilot. If you've seen that, you know what I mean. If you didn't, you should, because the ending is something else. Either way, in real life, such hopeful results are not really happening. People sometimes die, and we will look at the actual data from American statistical offices, and from the same period, like the movie, it will be the between 70s and 80s. So what do we have here? We will start again with the Jupyter Notebook. I have an Anaconda environment, as always, I'm not starting with a clean one because I've just tested does my notebook work properly. Either way, we have our airlines fatality problem. So let's we can really we have some. I have some lot of things here which will be reduced version for later, and what we are really doing here, we will be considering our data set, which is numbers of fatalities from from 1976 to 1985, from Statistical Abstract of the United States, and we'll be trying to create a model that will be able to predict for 1986, which we also have data, but also we will try to create such model that we will be able to analyze its entirety. We'll be able to analyze how creation of such model occurs, how we are doing it from start to the end. And let's look at our data set. Our data set is a table of 10 rows. Just a quick note, I've hidden some of the more technical not statistically related Python code. You can see it. You will be able to see it when you will be doing when you will be verifying it later. Either way, of course, if you want to, it will all be on GitHub. What you can do, what we can see here is this is our table, which for each year records the number of fatal accidents, the number of passenger deaths, and something called a death rate. Death rate is the number of passengers dying per 100 million of miles, because planes fly a lot during a year. And from that we can approximate the number of miles flown per year, which we'll be using later by dividing the passenger deaths by the death rate. The original data is available in Gelman's book, but also we'll see it here. The example is one of the exercises from the book. So generally we'll start with the most simple model that's possible. We'll be modeling our accidents with a Poisson distribution with an assumption that number of fatal accidents per year is generally fixed. So independent of a year, we have a constant probability of having having this number of accidents, and we will be trying to find such lambda, such a rate of our events that will be consistent with our data, so that our data will be distributed from this Poisson distribution. So our likelihood will be generally that y is conditional on just on lambda. So we start with the problem of creating such model. If having such model, we have a likelihood directly from the concept model, but we need to assign prior for our one parameter, and today we'll try this one nice technique of fitting certain useful distribution in order to get the parameters to fit our constraints, because we of course can do we can assign fixed constraints for our parameters, but those parameters that such things can be numerically challenging for our computational engine, in this case Stan, because which we will discuss in some the future. Stan really requires us to solve certain differential equations, and differential equations on bounded domains are difficult matters, and to be little precise, there are problems, and generally we want to just avoid the boundaries that we are sure that we will not be going there, and that's why we will try to get some constraints for our lambda. Of course, lambda has to be positive, so this is one of our constraints, which we cannot avoid. So we'll have to do some. We'll have to use the prior distribution with a bounded support of real numbers, but positive real numbers. But what we really are missing is the other end, and really we don't know much. We cannot do a lot of things, especially that we shouldn't really base our prior distribution on the data that we have. We can, however, look at least not on the output data. Maybe we can get some consideration from the covariates that we have, that our independent variables, like miles flown or time, but we shouldn't base it on actual outcomes, because that in such case we would be really using data twice. This can be done in certain situations, especially that we have a little data and we have to do something, but generally we should avoid looking too strong into data. However, what we can say about having a very little knowledge about airline fatalities, we are relatively sure that from even observing TV or on the internet, we don't have daily occurrences of fatal accidents in air flight. They are much rarer. Generally, it is commonly known, or at least it's a common knowledge that, or common opinion, that air flight is the safest way of transportation, because the least number of accidents happen. Just when something happens, a lot of people die at the same time, but actual accidents are very rare. So what we can do, when we can start with the assumption that having an accident, one fatal accident on the air flight once per day, or 365 of them in a year, it would be highly unlikely. And that would give us certain bounds on our prior. Of course, we could be even more restrictive, for example, reducing to once per week, but that would be stretching it a bit. We cannot be sure from our uninformed opinion that it is that there's no such accident per week. Per day we can be relatively sure. If it will be once per day, people won't be saying it as a safe method of transportation. So we will use our standard, our very known idea of having the relationship between standard deviation and confidence interval, that generally mean plus our plus 3 standard deviations give us 99% of distribution. So in this case, assuming that 365 or more should be not more probable than 1%, so that we are being open, we are not giving too restrictive option, but we want to have we want to play it on the safe side, that our distribution will be safe. So general idea is that we need to have lambdas that will be less than this. So lambdas lambda smaller than the value that fits this equation would give us the rate of less than probability of occurring 365 accidents per year would be have a very small probability. So we want to find a probability distribution that will just give lambdas that will be smaller than that. And first of all, let's determine what is the actual value of such lambda, and this is of course a quadratic equation for square root of lambda. We could either do a formal substitution, or we could just when we are interested in the positive result, we'll be doing some rounding. So generally we just use the polyroot function from NumPy, and this polyroot function solves us this equation in order to determine the square root of lambda, and we take a positive root of these equations and square it, so we would get lambda upper bound. And this lambda upper bound in our case would be 312, which is a number like so. what can we do now? Now we should choose a distribution that would give us positive values and that would assign values above 312 to be 1% probability above equal or above to 312 be less 1% or less. So a good idea, or like a simple idea for our case, would be half normal distribution. Half normal distribution is a generally absolute value of normal, in a sense, absolute value of, this is the variables that are absolute values of values sampled from normal distribution. All other ways, just positive half of the normal distribution, just multiplied by 2 in order to have an integral equal to 1. And this distribution is good for our case because usually, normal distribution has thin tails, so everything large above our 12 will be even smaller because the probability in the far areas of normal distribution is rapidly dropping. So a lot of probability is located in the center, and the farther away the probability is lower. So getting even more accidents would be less and less likely happening very fast. So half normal distribution for our case would be very nice. And how to choose such parameters of half normal distribution, and we can use it in Stan. This is an option that we could use any kind of equation solving system or numerical optimization system in order to find this, but Stan has one implemented. We can use it. This will be different options of what we can use in Stan, and we will be using Stan algebra solver, which is generally a nonlinear equation solver. And this nonlinear equation solver is documented in Stan documentation, and generally is a Newton method. This is a Newton method for solving equations. Of course, solving nonlinear equations has its own problems of multiple kinds, but really we are not. In our case, we don't need as much precision as. That precision is not really important because generally we will be far away from those tails anyway. And algebra solver can be used in more complicated Stan models. For example, you can have a situation that certain variables are related to each other by a nonlinear equation. And in order to evaluate the probability distribution, you would have to solve this equation. And if it doesn't have an analytical solution, and they don't usually have, you will need to use some kind of solver, which will have to be located in Stan in order to get the solutions iteratively in each probability distribution evaluation. So you can use it in many cases. What we'll be doing here, we'll just see how such model looks like, and it's not that complicated. But let's just check how it looks. So we'll have the general idea what's going on. So we are again we have a certain Stan model. I call this prior tune 3 because I was checking multiple distribution before, and the names are not important. In this case, we'll be having we'll need a target function. Target function of our function that will specify our equation. Our equation in this case is that 99% of probability is below. We have the condition of 99% probability is below 312, or using cumulative distribution function. Really, we are interested in this little part of cumulative distribution function in the end. So we want that the value of cumulative distribution function at our point, which will be 312, will be equal to 1%, and this can be computed using the, of course, normal distribution, just normal cumulative distribution function by operator multiplication. What we are actually having here is certain specifics of these functions that can work with Stan. So we are defining them in a function block, which has to be a first block in our model. And we have to define a function which will return vectors and take vectors and take certain vectors of values, vectors of parameters to be optimized, and we will need the and certain testing values that will be used in Stan. And these functions, this requirement of an API, so it's less readable that we will really look like. Either way, we need to compute, especially that you need even for one-dimensional equation, because it's a single-dimensional equation from one parameters and one condition. You need to return a vector from the equation. So generally, we want to fit this. Fit the distribution, so we have this condition. So this is our equation that probability of lambda being 312 or more is equal to 1, which we can get from conditions on cumulative distribution function. And the thing that might be surprising here, why this is exponent here, because in here we will be certain computation that's happening in the that are happening in our system is really the done on a logarithmic scale, and using such computations, using such logarithm, it will be much easier for us to compute things. There will be less problems in computation, especially in the Gaussian probabilities, because again, everything in Gaussians becomes very, very small, very, very fast. So when you are at logarithms, you are on a much more normal scale. It will be negative numbers, but they will be reasonable ranges. When you exponent them, then they will vanish very fast. So there's a big probability of numerical errors. And what we are here, we have data. So we will supply our model with an initial guess of what in our case sigma of our distribution should be, and we provide the probability that we're interested. So which value has to be above 1%? Why? Because we'll be using this function later in order to turn different distributions for further analysis of our model. So using block of transform data, we'll be able to compute our standard deviation, and we'll be doing it by these diagnostic elements of the function, and we'll be using function algebra solver, which has to be supplied with all those elements of the system. So it will be our distribution from the function block. It will be our initial guess. It will be our value that we are interested in to be not below 15. It will be above theta actually. Will be below theta, and I'll have to correct it later. And those two dummy variables that we are, and this will be print as values. And we'll be generating our quantities. Will be the sigma that we are interested in. So we'll just getting sigma from our model. And how we do it? We have to compile this model, because again, it's we'll need C code to do this computation. Of course, again, we don't have to use it in Stan, because we can solve this equation anyway that we want to. But I'm showing this for you because when we will be doing more complicated models that will require to solve certain equations, in order to evaluate the model value, you will have to do something like this. And the model is compiled, so not a problem. And what we are doing here, we'll create some kind of data. And this data will be our value that we want to have 99% of probability less than is our lambda upper bound, which we send here. Again, because here everywhere we have vectors, we'll also supply it with in the form of numpy arrays. And we give it initial guess. This initial guess has to be relatively large, because we're starting with large numbers, and we are using it in logarithms, because later we will need this for our computation. So we are sampling for our data, we provide seed, we provide our data, we use fixed parameters algorithm because our model doesn't have a parameter block, and we have only one iteration because we don't need to repeat it, we just need to compute it once, solve the equation once using algebra solver, and of course one chain because one more, and we get the from our parameters we get sigma, which will be an array, so we'll take it take a 0 element from this array, and the sigma will be 121. Of course, after a certain rounding, which I'm using this rounding, so it will be an easier number to write it instead. But it is really and it doesn't matter. It doesn't matter in case of these tails because there are so large numbers that we don't care. If we have some more specific situation, maybe we would have to be more precise, but not in this case. This case, our prior will be either way. We are still very far from the realistic numbers, so we just have this very weak bound of 365 accidents per year, and like if it's 364 or 366, it really doesn't matter. If it's the 1% probability of higher than that. That's not important. Data will skew us anyway. This is just to avoid some absurd situation of getting very large numbers very fast. So let's see how it looks like. So again, we can plot this our distribution. We are using standard normal distribution and that's why we need to multiply it by 2. So in order to plot it, we just need values, and using this sigma value, as you can see, the probability 100% is here, and this is our tail values. So all above that is 1% probability, circa about. And this is our that's how we tuned our prior. So our prior distribution will be a half normal distribution with sigma of 121. Half normal, so starting at 0 looks like this. Support is 0 to plus infinity, and 99% is located here. So as we did before, we start with doing some prior checks. We are not extending full possibilities of prior checks, but we just need to see if our priors give us something that makes a similarity of sense, that at least our data that we observed can be realized by our prior with not minuscule probability. So like such things can happen in our prior. That is a good starting point that our model is not absurd. If our data would be inconsistent with our prior, then we have problems. Those problems come either with our model, which we probably wrongly implemented. This is our first check. Then, if our model is well implemented, maybe our assumptions were wrong. And if our assumptions were not wrong, then either data is wrong also. But like, there is something called common theorem of I'm mixing the name. I'll check it later. But generally, there's an idea proposed by Professor Gelman that errors are usually fault of the model and not of the computation and other stuff. But like if the model is wrong, then something's wrong. Then the results are wrong. So we'll be doing prior predictive distribution to see what's going on. So what we'll be doing, we will simulate our we'll create a new model for prior predictive checks. So that's why PPC. It will be the naming conventions in here is Airline, fatal accidents, half normal, PPC. So if we use different prior means, of course, you can use your own naming conventions. I'm giving it here, so when you will be seeing my code, you will get some idea what's going on. So our model is again very simple in order to compute these stuff, because it is the our data will be just number of years analyzed, so we'll be able to sample more than one if you want to, and we will be sampling lambda from our half normal distribution, which is what is important here. You can add constraints in stand model at the generated quantities block. but those constraints will not be enforced. So if you put here constraint lower value 0 and you will put normal distribution, then those you will get errors. In order to, and first of all, you will get sampled from, you will have negative values that will be given to Poisson distribution, and that will generate samples. So you need to compute absolute value of normal distribution, of samples from normal distributions, which have then this nice option that they are just distributed as a half normal distribution with the same parameters. So depending on how many years we want to simulate, in this case, we just take the we are generating the vector of integers, and in a for loop we will be just sampling from Poisson distribution with parameter lambda that we sampled before. So having those, of course, like we again can do some sampling from our model, and we're going to compile our model, and we will do some sampling. We'll just do from one example here, and we will be using the fixed parameters algorithm again, because we have this here. So maybe like I'll just break lines so it will be more visible for you later. We are not using warm up because we are not really doing inference. We're just doing we are just sampling our model, and we have we are doing the same the refresh, and we have specified the seed. So we are sampling this our model. We get the sampling block, and of course we can repeat this sampling if we really want to, and we cannot because I haven't run it yet. So let's just run it. Okay. Everything is working, including Shift Enter, which wasn't working last time. Our plot is generated here. As you can see, here is the code for the. Just make it bigger. As you can see, this is how the algebra solver worked. It just didn't much time. This did this one iteration and gave us standard deviation of 121.126, which is rounded to 121. We read our model, we compiled it, which is stack, and we simulated it. And now it's did everything. And again, this no problem here. 1000 iterations happened instantaneously because we are sampling really from normal distribution, Poisson distribution, so nothing was interesting was happening, and we get our data. So we are using the extract method. We get from our model, we get our parameters, so lambda and simulated outputs, figures. How does it do? So our lambda parameter is of course consistent with our half normal prior because it was sampled from it. But like this is a check that our data generating model is okay, like not something strange is happening. So this is at the moment it's okay. Prior was generated, so it looks okay. Number of accidents. Here we can see the actual values that happened here. So they were all around 2030, and well, they are located in the most probable area. Their tails are filling the up to 365 accidents. So this is our data is our prior model is consistent with the data. The data are not something that would be impossible to happen in our case. Even like the more likely areas. Of course, our prior could be much more informative, and we could just be limited here. But again, we would need to have some kind of grounds why it was informative. So at the moment we also our very limited knowledge of airline crashes. Of course, if you would be doing such model for something real, then you would have to get more knowledge in order to get some more more prior information about what's going on, and get this knowledge from experts or learn yourself, or from or get it from other sources. So generally, you would have to need to do something like that. So our prior is okay. We can start doing some kind of modeling, and this kind of modeling we can use by creating appropriate stand model that will be able to infer the value of lambda. So what we are doing here? Here we have the data block, which is now supplemented with actual data of observed values. We added parameter block, which will be will give us the real the value of lambda, and here we enforce the constraints, so there will be no need for absolute values, especially that we give lambda as distributed as normal. So normal but with constraint, and that will give us the half normal distribution, which we then create our likelihood function that each of our y's of our outputs is distributed with a Poisson distribution with this lambda. So our likelihood will be each of these elements individually. And for extra kicks, we just simulate some outputs because we will need it for our prediction for 1986. So we'll just simulate the data here. We could use it only with one, but like I didn't want to change it now. So we'll have more samples of YSIM that's really needed. But we don't care about too much. Generally, there will be marginal distribution for each of those for m number of years with these assumptions of the model. So again, we compile our model. Maybe we'll just do it on the fly here. Just do this again. So it was some strange dependencies. We are having model. Compilation is needed because model is cached. You don't have a cache model in the repository, so you have to compile it yourself. And again, we are using the our data. So we are taking our data from our data frame that was defined above. This data frame was called Airline data. That's why it looks like a nice table, because Jupyter and Pandas plot nice tables. So this is actually a data frame, not a table. Not like a markdown table. This is just a data frame that is nicely visualized by Jupyter. And we are, so m is number of our rows, and y is number are our values of these fatal accidents. This is nice because such presentation, even if that is a Pandas series, it is being processed in a way that will be useful for stands. We don't have to convert it too much. And of course, we'll be doing some sampling using our model, using our data with a given seed. Then we extract our parameters, and again we will have a lambda and YSIM. And here a bit more is happening, but like really this problem is very, very fast. As you can see, gradient evaluation took 2.8 times 10 to minus 5 seconds. So 1,000 transitions in our models would take 0.28 seconds, and each of chains in B is being computed approximately around 300 at most 300 of seconds. So very, very, very fast, and our model was sampled and everything. Everybody's happy. We'll just compute some values for later. So we compute mean lambda and our confidence interval for lambda, and it was here that our mean lambda was now 23.92 with a confidence interval of 21.47 to 26.31. And here we have a complicated, very complicated graph. The sequence which we'll hold here, you could verify what's going on later. So what do we have here? First of all, in the context of our likelihood and our data, our posterior is much, much more thinner than our prior. Our prior in realistic aspects is really flat. Our consideration for lambda was like very far away from the data. So our prior was very flat, it was very non-informative. Generally, it's normal distributions with around with sigma around hundreds are very, very flat. So maybe some scaling is useful for modeling such processes. And let's see our 89% confidence interval for lambda. And as you can see here, it's most of the distribution located here. This distribution is kind of normal in its shape, or like bell-shaped either way. It's symmetric distribution, so you can see what's going on here. How the values are distributed. Most of the values are between those. 89% are here. Of course, we are using normal histograms. And our numbers of accidents, well, this is not that good to be like. Of course, our data are consistent with what's going on, but as you can see, they are very spread in these confidence intervals. So really, well, of course, they were differing by itself, but what's going on here is that our model is not very well corresponding to our original data. Our original data are possible in it, but not is what those dots represent is where these what was the value of accidents in a certain year, and if there are more than one here, it means just that the same number happened in the same year. So using this model for prediction, we have sampled even too many samples of posterior predicted distribution. So we have these predicted values of y, so we just need to compute the appropriate values, and we can use it by computing a median of it and having the again highest posterior density interval, and as you can see here, mean number of predicted accidents will be 24, median. Sorry, median of predicted accidents is 24, and our confidence interval is wide. As you can see, while the median is relatively okay, because in our prediction there were 22 fatal accidents with in 86, but we have large uncertainty about that. So maybe getting something. So maybe this is the too simple model, and this model is very simple because this model says us that whatever happens, the rate of accidents is constant. But looking from our data, the miles flown are not. Year after year, we fly more, with exception of 82. But generally, each year after year, the number of miles flown by a plane was rising in the period. The Flygskam concept of Scandinavia was not even in place yet. This is, if you haven't heard of it, it's a special word for a shame of having to fly, and flying, of course, is unecological and loses a lot of resources. So let's consider a better model that at least considers the numbers of flights per year or miles. So we can reformulate our rate in Poisson distribution, lambda, as an product of intensity, so how probable is aspect, with relation to exposure. Exposure is, so like, for example, how large a dosage in response how to this dose is for example, it could be deaths from certain poison. More the poison is given to the populace, then the intensity will divide how it's effective in killing the populace. In our case, the exposure will be, of course, number of miles flown, because the more you fly, the less likely you would die. Maybe that sounded wrong. Either way, we want to estimate the intensity. So now our model is still one parameter, the parameter is intensity, but for each of the years we will have different rates, because those rates will be proportional to our intensity and to our exposure, which we have in our data. So we are creating more complicated model, still one parameter model, but this model might be able to handle our data better, so give us better predictions. And again, we will need new prior. We still don't know much because we shouldn't use our data before and we haven't acquired new expert knowledge. So we will be doing the we'll assign the prior in the same way, but in this case, instead of lambda, we will use this product of theta and n bar. And n bar is a mean of miles flown. So we have some kind of estimate that in average, if we have an average amount of miles, our exposure will not give us the 365 accidents per day. As I said before, because this is very uninformative, it's not that important in this case. So we'll just do the same situation. Again, we'll compute the mean number of miles, and we'll solve set up necessary polynomial equation, which is here, and just scaled by mean miles here, so it will be computed nicer. And so we have a unit here with theta. We compute again root of theta. We are not rounding anymore because of we are much lower than 1 with our values, and our theta upper bound will be 0.055, which actually is a much longer number, but what we need here is what we are doing here is like just to give it some kind of visibility. And again, it's not that important, so we'll just keep it to 3 numbers before. And we'll again use our tuning function, because again we'll be assigning half normal distribution, but instead of for lambda, we assign it for theta, so it will be much thinner half normal distribution, because our scale of parameters will be much lower. So generally, everything is relatively clear still, and our model. Then what we needed to change, we need to change the starting point, because we are arriving in different areas of probability distribution of sigma, and all Newton methods require good starting points, especially in this case. We are in logarithm, we're in the small values. There will be some issues. We assign theta upper bound, we call the same function, which is again computed very fast, because we are just solving a one-dimensional equation with a Newton method, which is absolutely fast generally. So it takes us around 10 to minus 5 seconds. So very small, like 3.37 microseconds. Yeah. So very fast, and probably most of that was the handling of the printing statements. So this is what we've done here, and again we can compare how our probability distribution looks like, and it looks similar, but the scale is different. So again, it's a half normal distribution, but for values of theta around 0.55 is like this. So everything looks relatively nice. Actually, we could do it nicer. I should edit it out, but I really don't. It's not that important. Just look a bit nicer. And as you can see, so this is the. Well, we are just using the rounded value from here, and. Having this, we can now do probability distribution. And here, our model becomes a little bit more complicated. Maybe even not that much complicated, but we will need to use the create our model from what's going on. So again, the data is the same. No, the data is not the same, because we're doing probability distribution, and our probability distribution, we now need to incorporate in miles. And so our data includes the miles, and again, number of years analyzed. So for each of the years, we'll assign a certain number of miles, and we'll be generating our quantities in a way that, again, we will sample theta, not lambda, from this half normal distribution with sigma of 0.021, and we will be sampling our simulated values from Poisson distribution with a rate of theta times the number of miles. So generally we have some kind of Poisson regression here. And this of course happens, and compilation is not an issue, and we can sample it again very fast. Not much going on, because again this is a simple program. And we will now plot some things from what we wanted, and we have now let's focus on the distribution of theta. Why? Because now we will have to consider each of years separately, so we will not fit it in one figure. Here we have our half normal distribution. Again, this everything is consistent. Nothing was failed. Our sampling was okay. We've generated what we wanted to generate, and our theta is half normally distributed with required parameters. Now let's look at our simulated outputs, which we sampled for each of the years separately. As we can see, it is of course consistent with our previous before, and our data is consistent with what's going on, that it's possible or even around the around maximum value that we wanted. So everything is now is okay. Of course, as you can see, those scales might be differing a bit for the from year to year. At X scales here, maybe it will look better if we just add share X. I'm just specifying the plot so it may be clear. Okay, now we have everything in the same scale, and all those ticks are 365, and as you can see, everything looks very similar, and really our values are, this looks terrible because I've hidden the true values. So let's go back to the previous one. So as you can see, true values are happening where they should be happening. So everything, at least on the prior scale, looks okay. Like this, our prior distributions are not conflicting with our data, which was what we wanted. So let's start with the actual inference and seeing how our posterior predicts our actual data. So our model, which will be very similar as before to our previously used model for inference. This time we've added miles to it, so the name is appropriately changed, and we've adding the vector of miles, parameters theta. Our model computes the rates in the Poisson distribution, and our generated quantities are even here that we are sampling again for each of those years. So we'll be able to do the posterior predictive checks how it looks like in comparison to what we wanted. Okay, so model is here. As you can see, it's open. Compilation not needed. We are providing you again data structure constructed from our data frame. So we created a dictionary of number of rows, column of miles, column of fatal accidents. We're doing the fit with, let's see, we are extracting the parameters. Let's compute the necessary values. So we have the both mean theta and its confidence interval, which is given here, and we create again a nice plot of what's going on here. And this nice plot is we have very similar situation as before, but on different scale. So our lambda is again very thin in comparison to the prior, which was very wide, and our highest probability density distribution is here. And again, it's kind of centered, kind of similar, a bit more skewed maybe, but like this is something that will require further investigation than we want to do here. And let's do our histograms. And those histograms are again there are not that good results that we want. Of course, all our data happened here and are within the distribution, but there is certain effect that we can observe here, that for earlier years our model was underestimating the amount of data, the amount of accidents. So they are happening in the tail values. On the other hand, when we are approaching the 80s, now our model was, except of 1 year, 1982, which had, as we observed, less flights than a year before, it was underestimating all of the. It was actually a funny year because we, as you can see, we had less flights, but more accidents. So this was something that would require certain investigation of what's happening here, because this is something that's giving like a certain strange behavior. Of course, it's not like substantial difference number of accidents, but like with less flights, more accidents. So maybe looking what's going on, like what was the reason for that. Maybe we should, if we return to this model later, maybe we should need to consider something, what's going on. And again, what we are having here, except of 1982, after 80, our model was overestimating the number of accidents. So something is happening here which our model cannot capture, but it allowed us to identify that despite controlling for the number of miles flown, there is some effect that's here. Either at first we have more accidents than with less number of miles, and the more flights are going, the number of accidents is relatively smaller. So this is something that will require further investigation, and we will return to it in a lecture or two to see how it's going. But let's see how our model works for the prediction. And in order to do so, we will need to compute the number of miles from the data we have. We had a data for 1986, which was just not in our table. There were 22 fatal accidents with 546 passenger deaths and the death rates of 0.06 per 100 million miles. And we can compute miles from that. And we will be we need to create a new model, because our previous models were using our data for years before. So we need to use a model that will be able to estimate our value that we are interested in, because we are not interested. We need to get the value from that. So what we are having here is we are using the same model as before, but we've changed the generated quantities element of y in 1986. We just give the hard-coded value of 9,100 miles. We could do it multiple ways to do it. Even we could encode it prediction for 1986 as a missing data, but then our model would stop being a one parameter model, and this is not what we wanted here. And we just do the we have created this new model. We compile it, but it's compiled, and we again perform the inference, which was again very fast. So not much to do, not much to discuss here. And we have now can do some prediction, and as we can see, the mean, again, so here's the mean, so it's a median. Median of predicted the accident deaths is 38, which is much more than really happened. And again, the systematic effect that we've observed here is even more. Even more flights, and again, the number of accidents is much lower. So this is something, the seasonal effect or the time effect of that is happening. This is something that we would need to model and see what is going on, and we will do it in the next lecture. And so, as you can see, we have started with very simple model, which haven't told us much, except that we had a lot of uncertainty for our predictions. While we got the actual prediction wasn't that bad, the one we got before, we see that there's something more in the data. We've started doing the more complicated model that should work better. Actually, it gave us information that something is happening in this data, that if we want to reduce the inference, we have to model more. We have to create a more complicated model to extract additional information. And we will return to this example because actually this example was, I added it because I thought that the next example is too short, so I just need a 5-minute example of this exercise to show you. And this 5-minute example took around an hour, as I see, but like, let's go to the second example I want to talk with you, which is very closely related to Poisson to this one, because it's also based on the Poisson distribution. And we might do it a bit faster. This is an example of, again from Gilman's book, about kidney cancer. And kidney and actually the ureter cancer are very rare. And those cancers are, again, we have data from the 80s, and it's a very simple situation, very curious situation that when considering the flights, the counties in the United States, and observing the numbers of of deaths from those kidney and ureter cancers, there's a very specific situation. When you look at the 10 highest and lowest percent deaths in the entire population, there's something wrong. Something wrong is that looking at there's similar patterns of close neighboring counties, because like the county is a lower level than the state in the United States. At least that's that I assume. And the patterns are very similar, and those are caused by the fact that here we have the percentages. We don't have the number of cases. We have the how many cases per relative to number of population. And looking at that, if those counties here in the middle of the country are very small, and they are small around, they can be of population of 50 people, 100 people, 1,000 people, and certain cities are counties of population of 8 million people. So we have a lot of spread here, and this rate, while the rate of this is a rare disease, so when in large populations you would have rather good representation of this probability by having a very large number of people and modest number of cases. In case of small populations, if one case happens, then it's a drop, right? And if it's a small population, 0 happens, then it's normal. There's nothing happened, so we have a 0 case. So this is this will be those lowest cases. So again, such spreading doesn't look like here, and that's why we want to create a model that will be able to get some kind of information from that as to how to estimate this. And we'll be doing a modeling with an informed prior. So we will have the certain prior distribution that assigns us initial probability of having cancer, and we'll be modeling each county individually. We'll be modeling this county individually by having the number of death cases in there, which might be 0, and we'll have considered the 10-year period, because we're 10 years later, right? And we have our exposure, which is our population, and we have our intensity, so how often the deaths from this cancer happen. And we have an informative prior distribution for our intensity, which gives us information where it is located. And how this distribution was assigned, you can find in Gilman's book. It's not like a right way to do it. It's not right way to do it when evaluating certain cases, but in practical, but for our case, it was okay because it was done by moment matching. You can read it in the book, which I remind you, it's freely available, and the link was in the last lecture. So we will be moving to this case. So our cancer rate, I'll just move a bit faster, so we will not be doing it too boring for you, hopefully. And we have 3,700 counties. We are using the model I've showed you before with a gamma distribution, which, as you can see, there is a very low probability of death of this cancer happening. So this is the this probability is small, and this probability distribution give us some information. And we can, of course, repeat our idea to create some prior predicted distribution. So having our model, we provided the population, we sample from our prior distribution, we take theta, and using our model we sample how many deaths should happen for that population. And for example, for a population of 1,000 people, we can get such situation that we'll have between 0 and 3 deaths of that in the 10-year period, and we'll have the distribution is consistent, of course, with the with our prior. And it's like, as you can see, the mean rate of theta is also very well located here, is around 4 times 10 to minus 5. We have our data set. As you can see, the data set is, okay, so you will have it available if you want to play with it later. And we have here observed death rate per 100,000 people, which we won't be using that much. However, we have the population and death count for every county in a state and state pair here. So we have a county and a state. The name of counties can repeat, so you need to be aware of that when analyzing this data set. So those pairs have to be used together. And we are starting our work again with prior we've did our prior distribution for a single experimental town. So let's do it for our posterior estimation. So we have our model. We have the observed case at each observation of each county. We have a population of each county. We want to estimate our death parameters, and we are using a transport parameter block because previously we just assigned this theta times time exposure, our exposure times intensity directly to Poisson distribution, and in our case here we will save the parameters of lambda separately. So we'll create a transport parameters that is a function of in this case data and parameters, and that can be useful in order to, for example, see how the rates behave here, or it can be useful in order to do more complicated models, which we, for example, discuss in the next lecture, how transport parameters can be more useful, make model more legible, or multiple different things, or again those can be analyzed separately. So having that, our model uses transport parameter lambda. So as you can see, we assigned prior for theta, which is used in the transport parameters to compute lambda, and this lambda is used here. So it makes more and less legible at the same time. And of course, we are generating quantities, so we are sampling how many is possible from each lambda. We compile our model, and for example, we can do this test from here. As you can see, I've already extracted the values from the data frame directly as integer values from here. And for example, having one city, for example, counting number of 575 from our data frame, we get the data. So number of deaths and the population. We sample, we check those data diagnostics. Everything works nice. We can sample it. Everything works. And what we are doing here, in order to analyze all of those, well, there are certain issues, because we could create a big 3,700 parameter model, and it doesn't look that well, because there are some problems with numerics because of multiple rates, multiple size of populations, and we have larger populations of millions, and we have a small population of 50 people. The smallest one county has 50 people population, and in order to do so, we will have to do a lot of tricks in order to have it working, and creating a single model that will estimate all the parameters at the same time will be controlled. And of course, it won't be a single parameter model, so it will be very easy to code, but it doesn't work that well, and I don't see a reason for tuning it at the moment to get better results. So, in order to handle it better, I've just created a function that will estimate death rates and populations for each of the counties, and just providing it by appropriate county and population. It will return us a pandas series, which will then be able to append to our original data frame of what's going on here. So this is this computation that's happening here, and so we are just sampling, getting parameters, compute median of theta, median of simulated depths, and create the 90% in this case highest posterior density interval. And this function allows us to again, remember, the quantiles here as not, there is nothing sacred in 0.95. As long as you know what you are doing, you're consistent with single analysis, you can use 90, you can say 89%, you can use whatever you want. Just so it makes sense, so don't use 20% confidence intervals because it doesn't make sense. And we have this situation here. We just create this data frame. It doesn't look too pretty, but it fulfills its purpose. And for example, for this county before we can predict the date rate, predict the death count, and with error bars for each value. So getting the lower and upper bounds of the confidence interval. So what we are doing here, this will be for you when you try to run this code here, because you won't be provided with this file. You will be the function will be called and applied to our data frame. So it will just take values from our data frame, and for each row it will perform the appropriate computation and append right columns here. So our finalized data frame, which will be here, is given here. I just noticed that it will always, because I haven't been added save to the counts and estimates data frame, but this is like this. I'll add it later. You will, in the version you will have, it will be corrected. So it has, the data frame is appended by right values of predicted errors. And for example, from our county from population of 1,000 that we've sampled from initially in prior predicted distribution is Washaba, San Diego. Not really sure. Maybe I should left the full state names. Either way, you should that's why when non-American does analysis of American data. Either way, what we are doing here is we have all the information. So let's now observe how it looks in comparison to our previous work. And in order to do so, we will be computing our we'll be seeing how our data corresponds to our model. And to visualize that, we will be using an error bar plot. So the plot that gives us the interval for each of the variables, and we'll compute them here just from our columns of the matrix, just so it will be corresponding to the error bar function of matplotlib. And what we are having here we have our as a function we have the observed death rate, which we computed individually for this one, so on the same scale, and we have a predicted death rate. And what's going on? What's happening here is that in case of we have something called the effect called shrinkage, that we, in our case of our model, those values, those predictions from generally, if our model would be predicting actual death rate that was observed in certain counties, then all those points should be on this line. This line is the the relationship between death rate and like if death rate was predicted death rate was the same as the observed death rate, so the count of deaths to the population, then we would have location of this line. But this is not necessarily good representation, because there are certain counties that we have 0 observed cases, but still the cancer is possible. So then the prior takes responsibility for everything. And in other cases, when we have a lot of data, then our samples are being more drawn to the that our data is giving us something different than the prior, drawn us through the to the certain rate. So if we have observed information, then we have certain move here. And as you can see, everything is being drawn. For the higher rates are being drawn down, the lower rates are being drawn up to the to our prior, because our prior is an informative one, so it gives us where the expected deaths are, death count is located. And this prediction is not really like that special, especially that we have this prior that is not registered. But let's compare it to how our predicted death counts look on the population scale. And again, the larger number of population, we will have a large number of death counts, as you can see, fixed here in a logarithmic scale. And you can see that our error bars and our predictions for each of the populations, depending on the estimated death rate. And those death rates, as you can see, are much varying on the population, except on although the counts, because for larger populations, of course, the counts will be larger. And let's look at what's this point. This point shows that for a very large population, we have this very low predicted death count. Why is that? This is Los Angeles, and for Los Angeles, we have no reported values of our no reported deaths of this cancer, which is evidently a missing data point. This is not the actual statistics. They just don't have the information about it. If we've just drawn all the data together in order to estimate our death count, there will be a problem, because that will make the situation more difficult. And as you can see, still our prediction is not 0, it's moved away, because the prior, despite the very large population, still drawn us to a bit away from it. So it compensates from the death rate compensating with the populations to get us somewhere here. And it gives a predicted death count of 19, so gives us, there still is possibility of death counts here, deaths here, despite that the data, which is wrong at the present, says differently. And our model, on the other hand, very much better behaves as a prediction of actual deaths. So when we compare the prediction of death counts in the with the actual deaths with actual death counts, well, this situation is much different. And in this case, this model behaves much better, because despite the fact that the death counts are different than the rates we observe, but the rates are very noisy statistics. They don't give us much information, because either they are they can be skewed by some things. They are in only a certain observation, or for small counties they might be very problematic. For large counties, missing data points might be very problematic. And In our case, as you can see here, the correspondence of the predicted depths is very strongly linear. So generally, our model is very consistent with our error bars are wide, but they are capturing what is what's important here, and our predicted death count is very close to the observed death count. So our model is fit well, but there are some our models, because generally we have an assembly of models for each of those separate counties, and joining this data requires for more advanced approaches, for example, a hierarchical model, which might be doing later. So this is the here we have a zoom of this space here. So for very small amounts of numbers of deaths, as you can see, the cost is also here. However, as you can see, the error bar is standing more higher. Why? Because generally the model is predicting that prior says that the more deaths should be happening than that is was observed. So our prediction gives us the more value than higher value that was actually observed, especially for zero values, that something should be going here. So generally, what we had here, we took a model with an informative prior, and this informative prior allowed us to handle the discrepancies between large and small counties, because large counties have a lot of data or no data in case of Los Angeles, and their estimates are their estimates might be correct with response to actual model, but our prior keeping is everything in generally right points. And in case of smaller counties where we have very little data, probably no deaths, we still having this prior information, we know that this cancer is still a possibility, it can happen, and that's why. And in a hierarchical modeling approach, we will be estimating also the prior parameters for the cancer. So we'll be kind of estimating what is the probability of cancer in general in the group, and then using our data would have predictions for our certain areas. But this model that we might revisit on the later date. And finally, we are kind of exhausted all we can say about single parameter models. We haven't talked about Bernoulli distribution, which is a single binary trial. So it's like a binomial distribution, but only n equal to 1. So not that much that interesting in this case, but important for example, in case of classification on the stuff. So, but we will be doing it usually in connection with much more complicated models. So then Bernoulli distribution will make it return. And exponential distribution is good for modeling of waiting times. This is a continuous distribution with one parameter that determines its mean, and this parameter allows returns us real positive numbers. It's a slightly less more thick-tailed than half normal distribution, with a different shape because it's an exponential function. So the higher value, the lower probability. And I didn't have a nice case that will show us. Maybe we'll return to exponential distribution later. And of course, when you find literature single parameter models, you have the more complicated distributions, for example, normal, with some of the parameters fixed, and we'll just discuss all the parameters altogether. I think that we've discussed everything that we can say about those simplest models, that even if they are simple, still the consideration from the start to the end might be exhausting and might take us a lot of work. And again, the lecture that I've planned for 15 to 30 minutes took us an hour and a bit. So thank you very much for listening, and hopefully it was interesting for you. So thank you, and see you next time.